So I have a helicopter traveling at a constant velocity. So constant velocity should jump out to you immediately. Constant velocity means zero acceleration. Just make sure we definitely note that when we're drawing out the problem. Here's my helicopter. It's flying this way. I'll put velocity is constant. At the instant shown, the co-pilot releases a package from the helicopter. Okay, so if we release a package while we're flying, then that package is going to fly with, like, projectile motion, kinematic motion. So I'll erase that package for the moment. I'm just drawing my origin. That will be my satellite. This thing. The radar is tracking the helicopter. It records an angle of elevation to be 38 degrees. So we have 38 degrees here. The elevation to be 5,000. So we have 5,000. And the angular velocity to be 0.037 radians per second. So, if you didn't already know, just by kind of looking at that satellite and seeing our problem, you should know now. This is going to be one of the polar problems. We're tracking an object in motion using r theta coordinates rather than x and y. So I kind of got to be imagining this helicopter moving along, and I imagine that radial line that we're using to track it. And as our helicopter travels, I notice that our r is decreasing. The lengths of each one of these lines is decreasing as that helicopter flies along. So I know that r dot's going to be some negative number. Remember to break these symbols down. R dot really just means how our radius changes as time goes on. And the radius is clearly decreasing as time goes on, so I'm expecting whenever we work out our math, that number will be negative. In the same way, as that helicopter moves, my angle is going to be getting bigger. So theta dot, they actually give us that value, it's going to be a positive 0.037. Just make sure you're putting the correct signs on your numbers. Be very careful about that. Remember, speed is always a positive number. So if they tell you the speed of something, when you mathematize that and make it velocity for whatever your equations are, just remember, velocity is a vector. It could be positive or negative. Just make sure you're putting the correct signs on your numbers. For the instant shown, find the speed of the helicopter. Alright, so let's focus on that. So let's set up my coordinate system. This is not xy anymore. This is r, which is positive going outwards from our origin right here. And my tangential, my theta, my transverse, whatever you want to call it, axis will be this one. Here's my r. So here is the true velocity vector of my helicopter. I know for a fact that its velocity vector will be this, in this direction. I don't know its magnitude, I don't know the speed, how fast it's going, but I know it's got to be going in this direction, because the helicopter is just going to the right. And velocity is just where am I pointed at this instant. What is the tangent of my path? Now, this velocity is just in the I, it's just in the x. It's something in the I, 0 in the j. It's easy if we're thinking Cartesian, but remember, we're in polar form. What I need to do is I need to split this velocity vector into one component going in the r direction. This is going to be the r component of velocity, and the other component will be my theta component. Remember, components are just two smaller vectors that tip the tail add to get my main vector. So I set up my vector triangle here, and of course this vector triangle is a right triangle. So next I bring in my equation for velocity, but in terms of my polar coordinates. This is just the math for this same discussion we just had here. Here's the r component of my velocity, and here's the theta component of my velocity. So the nice thing is, this is a right triangle. If I just know one of the sides, as well as an angle, that's all I need. I can do sine, cosine, tangent. I could figure out my other sides of this right triangle. So, I'm sure I can figure out this angle, because I'm given this angle down here. So I'm sure I can work that geometry. So let's do that first. So I'm going to continue this horizontal line right here. This angle will be 38, just like this one is. That 38 is essentially just a horizontal line in my slope here. Well, here's a horizontal line, and here's that same slope continued. Therefore, this must be 38 as well. And because of geometry, this must also be 38. I don't know what you call it, but it's one of those theorems of geometry or something like that. So I know this is 38 degrees right here. So that's great. That's great. So they want to know this. This is our speed. This is our velocity. So I know I need to figure out either this one or this one to help me unlock this right triangle. I'm thinking I might have a good chance of doing that because theta dot I actually already know. That's great. Well, do I know r? Do I know the distance from my origin to the object I'm trying to track? Again, I'm sure I can work that. I'm sure I can find it. And here's a right triangle I can use to figure it out. So, we have our angle, we have an opposite, we want the hypotenuse. How about I use sine? So the sine of 38 will equal the opposite, which is 5,000, over the hypotenuse, which is r, which is unknown. We can figure out r with a simple calculation, and we'll get 8,121.3 feet. So I'm just going to put this over here just to save it. So this theta component of velocity will equal my r, which I know, times my theta dot, which I know. And we'll get for that 300.5. This will be feet per second. So that will be this component right here. So pretty much unlock this right triangle here. I can figure out my adjacent and I can figure out my hypotenuse. Let's go for the hypotenuse. Let's go for the speed because that's what they want in the question. The sine of 38 degrees will equal that theta component of velocity that we just found, the opposite, over the hypotenuse, which is our speed. So we can figure that out. And it's 488 feet per second. Alright, good. While we're right here, why don't we just figure out that radial component of the velocity. I'll use tangent. Tangent of any angle of a right triangle will equal the opposite, which I know, over the adjacent. And doing 300.5 divided by the tangent of 38, we'll get 384.6. Write that a little nicer. 384.6 feet per second. Now this is where we have to be really, really careful. VR is equal to r dot. But as I'm working through this problem, I'm not forgetting to break down these symbols. What do these symbols really mean? How is my r changing with time? Well, I know my r is decreasing with time. So r dot is really equal to negative 384.6 feet per second. Another way you could have seen this is when you're looking at our r component of velocity, notice that it is in the negative r direction. Here's our positive r direction. And because of that, you can put a negative here to say that, and then the math will give you the negative itself. But me, just every time I'm dealing with numbers, I'm always asking, alright, what does this number represent, you know? And I'm just making sure I know the significance. And if I have to, I'm putting signs on the numbers myself just to reflect what I know to be really going on. And in that way, I'm always keeping track of my answers. Right before I box that answer in and write it down on the paper, does it really reflect the reality of the situation? Alright, so we've squeezed all the stuff we can out of our velocity analysis of this helicopter. Part B is talking about the angular acceleration being recorded by the radar. So they really want theta double dot. So I'm going to move on to our acceleration equation. So, just like we split our velocity vector up, we're going to take our acceleration vector, which is either going to be going to the right or the left, and split that up into a radial and a tangential component. Same concept as before. Same thing really. But I can't forget, this thing is moving at a constant rate, which means acceleration is 0. So how am I supposed to add up two components, two smaller vectors, to get a result of 0? Well, the only way to add up two vectors and get 0 is if the two vectors are like this. And that's not the case here. These have to be perpendicular vectors. I mean, these are two different coordinate axes. So really the only way for this and this vector to add up and get 0 is if both of these vectors are 0 themselves. So this whole number, my radial component of acceleration, must equal 0. Same thing with this whole number. My theta component of acceleration must equal 0. That's actually really powerful. There's two equations forming up for us right here. This equal to 0 and this equal to 0. So let's write that out and see what we can do. So they want the angular acceleration. They want theta double dot. There it is right here. Well, I know we've gotten r. I know we've gotten r dot. And I know we've gotten theta dot. So this is looking real good. Alright, so we can calculate theta double dot. And you can see how important that negative sign is for that r dot. Sometimes if you mess up the sign, your answer comes out with the same number, just with, the opposite sign you were expecting. But in this case, you can tell that if we messed up that negative sign, we would get a completely different number for theta double dot. So I'm just always being careful when I put down my numbers, do they have the correct signs on them? So I do my math and I get 0.0035. This will be radians per second squared. Now looking at our r component, we know r, we know theta dot, so we could figure out r double dot, but they're not asking. I mean, they're asking how far away from the radar will that package be when it lands. Alright, so I'm just going to move on to tracking that package that was that was dropped. So we can write the kinematic equations that describe the motion of this package. It could either land behind the radar or it could land in front of it. So these equations are basically going to allow us to solve this problem. But you don't have these equations memorized, we can always derive them from first principles. So we'll start with x. The acceleration of this object in the x direction is going to be 0. And the reason for that is, if we imagine that package flying through the air, the only force on this package is its own weight. So, since there are no forces in the x direction, either the mass or the acceleration in the x has to be 0. And the mass is not 0, so the acceleration in the x has to be 0. So if I anti-derive here, I get that x dot, the velocity in the x, must equal some constant. And remember, you can always check yourself. If I take the derivative of this, what do I get? Well, I get back to that 0, so I know I'm good. And we can figure out what this constant is using the initial conditions. At time is equal to 0, what is our velocity in the x direction? And we already know that actually. That's this, the 488. So c will be 488. So not only at time is equal to 0 is our velocity 488, but for all time, as long as this object's moving, our x velocity is at 488. Alright, let me take another antiderivative, and I'll get that the position will equal 488 times time plus another constant. So at time is equal to 0, what is the x coordinate of this package? Well, I really should have done this from the beginning. I should have said, alright, let's make a coordinate system for the flight of this package, but I'll just make a coordinate system from the launch. I'll just say that this is going to be my x direction, this is going to be my y direction, which means at time is equal to 0, my package is obviously here, right where that helicopter is, which means the x initial is 0. If I plug in time is 0, x is 0, I must get 0 for that constant. So my full x equation is as simple as x is equal to 488 times time. Alright, so this is going to be a very useful equation. Let me just box it up. Alright, let's go through the motions for y. So I know that the acceleration in the y will equal the g number, which is negative 9.81 if we're in SI units, or negative 32.2 as we are here. So negative 32.2. I'll take an antiderivative. Y dot will equal negative 32.2 t plus c. Alright, at time is equal to 0. What is our y velocity? Well, at this instant here, if we zoom in there, if we really zoom in, my package is only traveling in the x direction. There's no change in y, which means there is no y velocity. So my c constant here will be 0. Alright, we'll take another antiderivative. The y-coordinate of this package will equal negative 16.1 t squared plus some constant. Alright, at y is equal to, at time is equal to 0, y is equal to, well, at time is equal to 0, my package is here, and here is at the y-coordinate of 0. So the c constant is a 0, and my finished y motion equation is this. Alrighty. So here's our plan. They want to know the distance from the radar when the package lands. So here's my package landing right here. And when it lands, my y-coordinate is negative 5,000. Alright, well, let's throw negative 5,000 in for our y and see what comes out for our t. What time does our package land? If we do that math, we'll get that we land at 17.6 seconds after we launched. If we take that 17.6 and ask the question, what is x at this time, we'll get that the x-coordinate of our package is approximately 8,600 feet. So, just by looking at that number, I don't know if we are farther than our satellite or our radar, or are we kind of before it? To answer that question, I've got to figure out this distance right here. And we can do that because right triangles. And I won't forget that we've already figured out that hypotenuse, 8121.3. So we're locked and loaded here. I'll do the tangent of 38. Tangent of an angle is equal to the opposite over the adjacent. We'll figure out that adjacent, and we'll get approximately 6,400. So my x-coordinate is 8,600, which is a lot bigger than 6,400. So I know I'm landing behind the radar. And if I just subtract these two lines, my 8,600 minus my 6,400, I'll get this distance here that I want. So my distance will equal 8,600 minus 6,400, and we'll get 2,200 feet. And that is our final question answered right there. So, hope this problem made sense. Definitely a lot of math stuff as well as conceptual stuff driving this problem. Feel free to ask any questions you may have.